Hi everyone, my name is Wenhan Wang and I'm a PhD student at Peking University. I'm glad to present our paper, Modular Tree Network for Source Code Representation Learning. When using deep learning for program comprehension tasks, researchers often use ASTs to model the structural information of source code. Previous works have successfully applied tree-structured neural networks, such as TreeLSTM and TBCNN on ASTs. These models use a tree neural network unit to operate on depth-2 subtrees, which is a node and its direct children. The subtrees in ASTs are defined by different grammar production rules, so these subtrees can be significantly different in structure and semantics. However, existing tree-structured neural networks use the same neural network unit for different structured subtrees, making these models hard to capture the differences between subtrees. To address this issue, we plan to use different neural network units to model different AST subtrees, which leads to the main idea of this paper. In this paper, we propose a new tree-structured neural network, Modular Tree Network for learning representations of ASTs. Basically, MTN follows the structure of TreeLSTM. It calculates the states of all AST nodes in a bottom-up manner and uses the state of the root node as a representation of the complete AST. Each MTN unit consists of two components, a neural network module specific to different node types, and a container similar to TreeLSTM. For node J, the neural module first chooses a neural network function based on the type of J and uses the chosen function to aggregate the state of all J's children. The container, like TreeLSTM, uses the aggregated children state to update the state of J with an LSTM cell. In MTN, one key question is that what type of subtrees should be equipped by special modules. In this paper, we choose subtrees that contribute to the high-level structure of programs. For example, in C language, these subtrees include function definition, while, do-while, for, if, switch, case, and sequences of statements. Another question is how to build different modules for these different subtrees. For function definition, while, do-while, and switch, these nodes have two children, so we use a basic recursive neural network as their module. A for node has four children. The first three of them control the execution of the loop body, so we use a two-layered recursive neural network as a module of four nodes. And each node may contain two or three children, based on whether it contains an else statement. So we build two different modules for these two situations. There are also some types of nodes which can have a sequence of children. For these nodes, we use an LSTM to model their children's states. For the node types we don't mention before, MTN simply uses a basic child sum TreeLSTM unit to model their subtrees. For the container parameters of MTN, we propose two different strategies of parameter sharing. In the first one, MTN-A, all MTN units share one single group of parameters. In the second strategy, MTN-B, container parameters are only shared within the same type of nodes. In order to evaluate the performance of MTN, we conduct experiments on two different tasks, program classification and code clone detection. For program classification, we propose a new dataset which contains 293 classes of programs from an online programming platform, POJ. In clone detection, we adopt the existing dataset, OJ-clone, which was previously used in several clone detection researches. In this paper, we use the cosine similarity as a similarity measure of the representation vector of programs. If the similarity between two programs are larger than 0, Then we predicted them as a true clone pair. If the similarity is lower than 0, we predict them as false clones. Here are some of the detailed settings of our experiments. We compare our MTN against existing deep neural networks with sequential tree or graph structures. Now let's have a look at the research questions and results. First, for the program classification task, we can see that MTN outperformed all baseline models on our classification dataset. For the clone detection task, the results are similar. MTN achieves better precision, recall, and F1 than all baseline models. In both datasets, MTN-A and MTN-B achieve similar results. We may notice that for most baselines, the precision and recall are highly unbalanced. This is because for models like TreeRSTM, setting 0 as a similarity threshold is not the best choice. So we additionally present the precision recall curve when we gradually change the threshold from -1 to 1. From the PR curves, we can see that when precision is the same, MTN model have a higher recall than TreeRSTM in most circumstances. The next research question is how does each module of MTN contribute to our results? To answer this question, we perform an ablation study on the clone detection task. Each time, we separately remove an MTN unit from the MTN-B model and replace it with a traditional child sum TreeRSTM unit. The results show that removing the sequence module leads to a significant drop in clone detection metrics, while removing other modules have a smaller impact. As MTN need to build different structured neural network for different AST inputs, a key issue of MTN is its complexity. Here we compare the time and memory efficiency of MTN against TreeRSTM. From this table, we can see that the running speed and memory cost of MTN is similar to TreeRSTM, which is an acceptable result. In conclusion, we propose a modular tree network to learn representations of AST. MTN consists of several modules designed for different AST subtrees. The experiment's results show that using different neural network modules to model different subtrees can achieve better performances on both program classification and clone detection. In the future, we plan to apply MTN to other programming languages and explore the possibility of dynamic batching to increase the time efficiency of our model. Thank you very much for listening to my presentation.
Good afternoon again. The speaker of this very nice paper is Wengang Wang from Peking University in China. The paper is a journal first paper. This research has been published in Transaction on Software Engineering. We have a question from the audience, and the question is what may be the key reasons why modular tree network would perform better than tree-based CNN? What may be needed to adapt MTN to other tasks, for example, bird detection or different programming languages?
Okay, thank you. I think the main advantage of modular tree network over tree-based CNN is that MTN uses different neural network submodules for different subtrees, such as different modules for loops and while loops. However, in tree-based CNN, It only uses a single kind of neural network unit for all subtrees. I think MTN can be adapted to other tasks like bug detection. Actually, recently I have done an experiment to apply MTN on a defect detection dataset in C. For adapting MTN to different programming languages, I think it's possible, but we need to build different neural network modules for different programming languages. For example, a for loop, the grammar of a for loop in C and Python is different. So we need to build different models for these two different languages.
Thank you for the answer. We have another question from the audience. This question is from Yusufumi Suzuki. How do you decide structure of MTN? Can you so we have indeed a couple of questions from Yusufumi Suzuki. Can you generalize it for different programming languages? Of course, both the questions are related one another.
Okay, thank you. I think when building different modules in MTN, we need to consider the syntactical structure of these subtrees. For example, in a code block, the children know in the code block is a sequence of statement. So we use an LSTM to model this sequence. So for generalized MTN to different programming languages, I think I have already answered it in the last question. I think it's possible to generalize to different languages, but we need to build different modules based on the structures of ASTs for different languages. Thank you.
Thank you very much for your nice answer. There is someone else in the audience that would you like to formulate a question for Wenan? Okay, I have a couple of questions for you.
Okay.
So you propose a modular tree network that dynamically composes different neural network units into tree structure based on the input output syntax tree. You then evaluate your model on two kinds of tasks: program classification and code clone detection. To do this evaluation, you needed to use some dataset. So my question is about external validity, and more precisely, my question is: do you believe that user dataset as a dataset have affected the results?
I think in this paper, we use a dataset in C language from an open judge platform where the student submits the answer to some programming question. I think using student programming context to evaluate the performance of program representation model is very common in previous works, such as tree-based CNN and several other works.
Indeed.
So,
My
Well,
question was, do you believe that the use of the data set in some way affected the conclusion, right conclusion, so a kind of conclusion validity threat? If I will remember, I gave a look to the paper, and for program classification, used a data set annotated by students on C programs, right? So this can affect the results in an undesirable way. This is what was I meant in my question. Okay, I have also another question, and concern the second kind of application of your approach, and mostly you applied your approach, your solution on code clone detection. You know that there are four kinds of code clone detection,
yes.
type one, from type 1 to type 4. And my question is, on which of them do you focus your research, your empirical assessment?
I think now I currently focus on type 4 clone
Mhm.
because in the data set is already deduplicated. So I believe there are no type 1 or type 2 clones existing in the data set. And
Of
the
course,
number of
of course,
type
but
3 clones are
yeah, but
small.
you called chose a different data set. There are a number of data set for type 1 and type 2 clones. So my second question concerned the generalizability of the results. So do you believe, if I well understood, you are saying that your approach can be also applied to different kinds of of clones, right? From type 1
Yeah.
to type 3. Can you elaborate a bit more on that, on this, on this point, please?
Sorry, I cannot fully understand your
O-
question.
Okay. You said that you used you focused on type 4 clones because your data set contained only this kind of clone, right? Do you believe that your approach can be also applied to different kinds of clones?
Yes, I think because the first three type of clones are easier to detect than type 4 clone.
Yeah, you are right. Type 4 is more complicated to detect than the other kind of clones, even if type 3 is not so easy to detect. Well, thank you for